In the vast expanse of the universe, where stars shimmer like diamonds in the velvet sky, and planets drift in perfect harmony, there are creatures that defy our understanding, that hide their mysteries deep within their black hearts. These creatures are black holes, born from the death of massive stars, and they are the masters of their own realm. Nothing can escape their gravitational pull, not even light itself. They are like cosmic vacuum cleaners, sucking in everything that comes too close. But black holes are not just destroyers, they are also creators. When they devour stars and planets, they release enormous amounts of energy, and this energy can give birth to new universes. Within a black hole, the laws of physics as we know them break down, and the fabric of space and time itself is warped beyond recognition. In this bizarre and surreal landscape, new universes can be born, each with its own unique set of laws and properties. The process by which black holes create new universes is still largely a mystery, but scientists have theorized that it involves a combination of quantum mechanics and general relativity. As matter is sucked into a black hole, it is stretched and distorted by the immense gravitational forces at play. At the same time, the energy released by this process can trigger a chain reaction of events that ultimately lead to the formation of a new universe. But black holes are not static creatures, they evolve and change over time. As they consume matter, their mass increases, and their gravitational pull grows stronger. This can cause them to spin faster and faster, until they are rotating at nearly the speed of light. At this point, they emit enormous amounts of energy in the form of jets of gas and particles that shoot out into space like cosmic fireworks. As black holes evolve, they can also merge with each other, forming even larger and more complex structures. These mergers can release enormous amounts of energy in the form of gravitational waves, ripples in the fabric of space and time that can be detected by instruments on Earth. The study of black holes and their role in the creation and evolution of universes is a fascinating and complex field that is still in its infancy. But with each new discovery, we inch closer to understanding the secrets of these cosmic behemoths and the role they play in shaping the universe we call home. Despite the similarities between these two singularities, there are also important differences. The singularity at the center of a black hole represents the end of a star's life, while the singularity of the Big Bang represents the beginning of the universe. Additionally, while the singularity of a black hole is localized to a single point in space, the singularity of the Big Bang is thought to have occurred everywhere in the universe simultaneously. Overall, while there are intriguing connections between the singularities of black holes and the Big Bang, they remain separate and distinct events with their own unique properties and mysteries. The Grand Unified Force is a powerful and enigmatic force that may have existed in the early moments of the universe. It is believed to have been a singular, unified force that governed all of the fundamental forces of nature, including electromagnetism, the strong and weak nuclear forces, and gravity. In the Grand Unified Force, all of these fundamental forces were thought to be indistinguishable from one another, existing as one cohesive and unbroken force. It is thought that as the universe expanded and cooled, this unified force broke apart into the separate forces we know today, creating the distinct and separate nature of the universe we observe. Despite the fact that the Grand Unified Force is a hypothetical construct, it is an area of great interest to physicists and cosmologists alike, as it holds the potential to unlock some of the most profound mysteries of the universe. By understanding the properties and characteristics of this elusive force, we may be able to better understand the fundamental nature of the universe itself. The Grand Unified Force is thought to have existed in the earliest moments of the universe, when it was a hot, dense and rapidly expanding state known as the Big Bang. It was during this time that the force is believed to have unified the fundamental forces of nature, creating a singular and all-encompassing force that governed the early universe. As the universe expanded and cooled, the Grand Unified Force began to break apart, separating into the four distinct fundamental forces we know today. Electromagnetism became the force that governs electrically charged particles, the strong nuclear force became responsible for holding the nuclei of atoms together, the weak nuclear force was found to be responsible for certain types of radioactive decay, and gravity became the dominant force on large scales. The Grand Unified Force is an area of intense study, as it holds the potential to unlock some of the most profound mysteries of the universe. By understanding the properties and characteristics of this elusive force, scientists hope to gain insight into the early moments of the universe, the formation and evolution of galaxies, and the ultimate fate of the universe itself. The life cycle of a black hole begins with the collapse of a massive star. When a star with a mass several times greater than our Sun runs out of fuel, it can no longer produce the energy needed to counteract the force of gravity. As a result, the star's core collapses inward, creating an immense gravitational field. At this point, the star becomes a supernova, exploding in a brilliant display of light and energy. The outer layers of the star are expelled into space, while the core collapses inward to form a black hole. As the black hole forms, it creates an event horizon, a boundary beyond which nothing can escape, not even light. This event horizon is determined by the mass of the black hole. The more massive the black hole, the larger the event horizon. Once a black hole is formed, it continues to grow as it pulls in matter from surrounding space. As matter falls into the black hole, it becomes compressed and heated, emitting intense radiation that can be observed from great distances. Over time, a black hole will continue to grow as it pulls in more matter from its surroundings. However, as the black hole grows, it also emits intense radiation, causing it to lose mass. Eventually, the black hole will stop growing and will reach a stable size, known as the Schwarzschild radius. Once a black hole reaches this stable state, it can remain there for billions of years, emitting only a small amount of radiation. However, over an extremely long time, the black hole will slowly lose mass through a process known as Hawking radiation, named after physicist Stephen Hawking. As the black hole loses mass, its event horizon will shrink, eventually reaching a point where it can no longer sustain itself. At this point, the black hole will evaporate in a burst of energy, releasing all the mass it has accumulated throughout its lifetime. The event horizon of a black hole is the boundary beyond which nothing, not even light, can escape the immense gravitational pull of the black hole. It is essentially the point of no return for anything that falls into the black hole. At the event horizon, the escape velocity required to leave the gravitational field of the black hole is equal to the speed of light. Therefore, any object that comes within the event horizon is inevitably pulled into the black hole and is lost forever. The event horizon is an important concept in the study of black holes, as it defines the boundary between what is visible and what is not. Anything that falls into the black hole is hidden from the rest of the universe, and all information about it is lost. Holographic universe theory suggests that the information that is lost at the event horizon may not be entirely lost after all. This theory proposes that the universe is like a hologram, in which all the information contained within a volume of space can be represented as a two-dimensional image on its boundary. According to this theory, the event horizon of a black hole is like the boundary of a hologram, where all the information about the objects that have fallen into the black hole is encoded on the surface of the event horizon. In other words, holographic universe theory proposes that the information that is lost when objects fall into a black hole is actually contained on the surface of the event horizon, like a holographic image. This theory has profound implications for our understanding of the nature of the universe and the fundamental laws of physics. In recent years, researchers have been exploring the connections between holographic universe theory and the physics of black holes. Some studies have suggested that the event horizon of a black hole may be like a holographic projection of the information contained within the black hole, offering a potential way to reconcile the apparent paradoxes of black holes and quantum mechanics. The theory that suggests new universes are formed from black holes is called the black hole cosmology hypothesis. This hypothesis suggests that the formation of a black hole could create a new universe, separate from our own, which could potentially have its own unique physical laws and properties. According to this theory, as matter falls into a black hole, it becomes compressed into an infinitely dense point known as a singularity. At the singularity, the laws of physics as we know them break down, and it is believed that new physical laws may emerge. The black hole cosmology hypothesis proposes that a new universe could be born from this singularity, as the compressed matter explodes outwards in a massive burst of energy, creating a new universe with its own unique properties. This new universe would be completely separate from our own, and could potentially contain its own galaxies, stars, and even life forms. In addition, the theory of the multiverse suggests that our universe is just one of many possible universes, each with its own unique physical laws and properties. The multiverse theory proposes that there may be an infinite number of universes, each with its own unique characteristics. The evolution of universes in the multiverse may occur by design through the process of natural selection. According to this idea, each universe in the multiverse has its own set of physical laws and properties, which determine how it evolves over time. Those universes with physical laws and properties that are well suited to the formation of stars, galaxies, and life forms are more likely to evolve and persist, while those with less favorable conditions are more likely to collapse or be unstable. This process of natural selection in the multiverse could lead to the creation of universes that are finely tuned for the emergence of life, suggesting that the existence of life in our own universe may not be a coincidence. As we delve deeper into the mysteries of the universe, we uncover wonders that leave us in awe and immersed. From the depths of black holes to the birth of new galaxies, we seek to understand the forces that shape our realities. The singularity, a point of infinite density and mass, holds secrets that challenge our knowledge and surpass. The grand unified force, a theory that seeks to unite the forces of nature that govern our cosmic sight. The black hole cosmology hypothesis, a daring idea, proposes new universes from black holes that appear. And in the multiverse, we see a tapestry of possibilities, each universe a unique expression of cosmic identities. As we ponder these concepts and theories with fascination, we realize the limits of our current human comprehension. Yet, we press on with curiosity and an unyielding spirit, to uncover the secrets of the universe, and in them find merit. For in the study of the cosmos, we find not just knowledge, but a sense of wonder, awe, and a sense of cosmic heritage. So let us continue to explore, discover, and marvel at the unknown. And in the mystery of the universe, find a sense of home.